Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GHEtool Cloud. And today we will be releasing modulating heat pumps into GHEtool Cloud. Now, if you've been following us for a while, you know that this has been a long-awaited feature. Back in the summer of last year, we started a three-part improvement series on GHEtool, where first we made the fluid properties variable over time, making sure that we were able to accurately calculate both heating and cooling with our geothermal systems. Last month, we added on top of that variable flow rates, where we now no longer work with a constant flow rate, but your flow rate can vary from hour to hour in heating and cooling separately, making sure that also in these mid-seasons we get a very accurate picture of what our geothermal system behaves like. And today we will be covering the third part of this improvement series, namely stepping away once and for all from this static efficiency assumption towards using modulating heat pumps with part load and temperature dependent data. Now, before we jump into GHEtool and show us around a little bit, let us talk a little bit about why or what the assumptions are behind traditional bore field design. Now, as you perhaps recall, we typically work with a building load, which one way or another needs to be converted towards a ground load to calculate, the temperatures of your bore field itself. Now, typically, historically, this has been done by using official SCOP values, seasonal coefficient of performance values. Now, if you have not watched our video related to heat pump efficiencies from last year, it's linked in the description below. But typically, these come into two different variations. You have the B0W35, typically for low temperature emission systems, and then B0W55 for the production of domestic hot water. Now, using these constant efficiencies, we convert the building load towards the ground load, but there is a problem. Namely, we use these values to convert both the peak powers and our yearly energy demand. But the peak power is not represented by these seasonal coefficients. It's the coefficient of performance that you need for that. And by using the SCOP to convert your peak power towards a ground load, you're overestimating how big your peak power will be on your ground. So you risk oversizing your geothermal system. But on the other hand, as you can see, these efficiencies are given at B0, meaning you get 0 degrees into your heat pump. But typically, especially in the first years of operation, your heat pump works at way higher temperatures. So your efficiency is also higher than your official documentation tells you, meaning that your imbalance due to this higher efficiency will also be higher. So perhaps for your particular project, you risk undersizing it. And a third problem with this constant efficiency approach is that your design basically does not matter. And what I mean by that is, since efficiency is an input, no matter how deep you drill or how many boreholes you install, your efficiency of your system will not change, which is counterintuitive to, basically the reality of such systems, because we know that their efficiency depends on temperatures and part load conditions, etc. So that's why we work together with heat pump manufacturers to get as much efficiency data as possible from them and to implement it into GHEtool Cloud. Now, why should we want to design with these dependent and these variable coefficients of performance? Now, a first reason is that we want to be able to do more advanced simulations. We want to gain more insights from our simulations. Basically, we want to see how changes in design, for example, drilling deeper or so, reflects on the efficiency of a geothermal system, the coefficient of performance. Next to that, we want to be able to compare part load efficiency with full load operation and compare different heat pumps with each other. And thirdly, we also want to see what the effect is of heat pump oversizing. Because typically, although it depends from machine to machine, your heat pump's highest efficiency power is not at full power. It's not at 100% maximum load. It's typically somewhat lower, between 60 and 80%. So meaning that if your heat pump is slightly bigger than your actual building demand, it can be that your system will have a higher seasonal efficiency and hence a lower electricity cost. So these are all things we are now able to play around with in GHEtool Cloud. And most importantly, perhaps for your user, is to showcase to your client the real efficiency of a ground source heat pump when compared to an air source heat pump. Because as we said before, and it's linked in the description below, when we talk about seasonal coefficients of performance, we see that our air source heat pumps are becoming better and better. And we know that in reality, our ground source heat pumps still are better, but this is not reflected in the official data. But by being able to calculate with it, when you design your bore field, you will be able to showcase the real life efficiency of your ground source heat pump for your particular design. And if you make a different design, you will also see that reflected in your results. So I'm really excited. Let's jump into GHEtool together and let's show what's new and what insights we can get from it. So here we are in GHEtool Cloud. I created a brand new project. So let's look around what we can do with this new modulating heat pump feature. So we're going to calculate the temperature profile first with some temperature limits. We'll use a bore field of 5x4 boreholes, 150 meters deep. So a regular rectangle for this case. We have a W tube, 25% of monopropylene glycol, and a constant flow rate of 0.3 liters per second to keep it simple for now. The thermal demand. First, we will work with a constant efficiency as before, 3.41 as an SCOP for heating. I'll come back to that number later. And some passive cooling. And our total heating and cooling demand is 100 kilowatts heating, 40 kilowatts in cooling, with 200,000 kilowatt hours per year of heating and only 40,000 kilowatt hours per year of cooling. So it's a rather big project. Now if we go to the results, we see our temperature profile here for 20 years and our Sankey diet. So that's our first situation. Now, as you can see, for thermal demand, it's not possible to work with our database. And that's because if we want to use these modulating heat pumps, we need to have hourly data. We need to know what the energy demand at every hour is, because we need this information to look up the real efficiency at this working point to calculate in the end the overall efficiency of your system. So we need hourly data. Now, luckily for us, GHEtool has a built-in feature to calculate hourly data even when you don't have it. So let's call this scenario 2 hourly data. And let's create an hourly load. We will do this based on our location. Now, this project was located in the city of Brussels in Belgium, but it does not really matter. Here we have our assumptions, so 100 kilowatts cooling, in heating, in cooling, and so forth. And let's now generate an hourly load. Now, if you don't know how this works, we have an old video about it. It's linked in the description as well. So let us go ahead and use this profile. And now we have the option to also work with a database. Now let us first, as a comparison, calculate it first with the constant efficiency and duplicate this scenario to work with a heat pump. So let's call this scenario 3, heat pump. So this was the data before with now our hourly load values. Now let's go to the database, and here we have our heat pumps implemented. Now at the moment, the heat pumps you see here are from the Swedish company Enrad. They already provided us with detailed temperature and part load dependent COP data. Other manufacturers will also follow in the near future, but at the moment we have these Swedish heat pumps. Now, let's see, we know that we had a system of 100 kilowatts, so select their HP 500 heat pump for now, which is rated to 111 kilowatts. Let's use passive cooling. You can also use active cooling, but in our case, passive was enough. And now we will simulate these systems. Now, what it will do basically is it will calculate the temperature at every hour, calculate the efficiency there, and then update our building load so we end up with a certain temperature profile. Now, this is the profile we end up with. And what you can see is that our minimum temperature is actually significantly lower than we had before. And that is because our efficiency of our heat pump, which is given here, it's 4.62 on average over the whole simulation period. Now, GHEtool calculates it also per year. So you can see that we start with more than 5 and we go down to 4.5. And we go down because there is this imbalance or ground cools down year after year. So this has an effect on your efficiency as well. And now with this part load data implemented, you will be also able to see, okay, if I do some regeneration and I compensate for this imbalance, what would be the effect on our efficiency? How will our efficiency of our heat pump improve? Now, here it's also stating a warning message. Because we're now working with particular heat pumps, it can be that you select a combination of heat pumps that is not being able to fulfill your whole building demand. So if we scroll down, we see that we have a shortage of power. Yeah, because of course, depending on the temperature of your ground, your heat pump is able to deliver a maximum power. And in this case, in the last year, this heat pump will be short of 7 kilowatts during, I believe it is 1 hour of the simulation periods. So it does not really matter in this case. But for example, if you have a system that needs 200 kilowatts and your heat pump can only deliver 150, in that case, you will see here a significant power shortage. So that's the first insight, how this efficiency changes over time. Now, let us go ahead and use another heat pump. Because now we used a heat pump rated at 111. Let's call this 2 heat pumps. Let's go back to the thermal demand, and instead of working with one machine, we can also opt for a cascade configuration of 2 smaller machines. And the advantage of doing that is that, as we discussed, and we have a slightly higher maximum power now, but also having 2 machines can increase the efficiency of your overall heat pump. And here we are. So we see that the temperature is now even lower. And that is due to the fact that our efficiency is now higher. So we're not at 4.6, but with these 2 heat pumps combined, we're now at 4.9. So also there is another flexibility with being able to using these heat pumps directly. You can combine different heat pumps, oversize them a little bit, undersize them, and see what the effect on your efficiency is in the end. Now, let's make this design a little bit better, because now we're going to negative temperatures. So let us go ahead and duplicate it again. Let's keep these 2 heat pumps, but now let us go to the bore field tab, and let's say, okay, go to 2 boreholes and make it, for example, 300 meters deep. Of course, we also need to change flow rate. What we basically did is we went from 20 boreholes to 10 boreholes, so we double our flow rate in our system. And let us go ahead and simulate that again. So now what we are looking for is how does the efficiency change when our bore field design has changed. So here we see a significantly higher temperature. Because now we have an average undisturbed ground temperature, which is significantly higher. So all our lines are better, but also, as you can see, our heat pump efficiency is now almost 5.4, where it was 4.9 in the past. So also changing your design, changing your depth, the number of boreholes, the flow rate, etc., will now impact the efficiency of your heat pump. So you will be able to design systems with way more flexibility and so forth. Now, a last thing I want to say before we wrap up this video and you can have a go yourself, is that this module is compatible to the calculate temperature profile, but also the two functionalities to size your system, both the required depth and the required size and depth. But it can be rather slow, and that's because we're now not only updating the fluid properties every hour, but also the efficiency every hour. And when the efficiency changes, also your ground load changes, and we need to iterate and iterate until we converge. So it can be quite slow for these two methods. For the calculate temperature profile, you've seen it, it goes fast, but these two methods can be a little bit slower. So we suggest at the moment that you just use this method to calculate your temperature profile, do a really in-depth simulation of your temperature profile, and use these methods at the moment still with a constant efficiency to speed up your workflow. Now, let's go back to the slides and wrap up this video. So I hope it is clear what the added benefits are when you're working with modulating heat pumps directly when you're sizing your geothermal system in GHEtool. But this is not the end of the innovation, it's just the beginning. Because at the moment, these modulating heat pumps are only compatible with hourly load data. And because, as we said, we need to know the power at each hour in order to find the right efficiencies and to calculate the correct ground load with it. But we're already improving this method in the backend so that it can be extended to working with monthly loads later on. But in the meantime, you can rely on the functionality built in GHEtool to calculate your hourly load profile based on yearly estimates. A second thing we will be working on this year is to make these modulating heat pumps also compatible with our optimization methods. Because now there are two different philosophies, let's say. On the one hand, you can work as we showed with selecting a couple of heat pumps and simulating your system and playing around with it. But on the other hand, our optimization methods, they determine for you what your optimal power will be. And at the moment, these are two different philosophies, two different ways, and we are working on a way to combine them so that you can say, for example, I want to have a selection of this, and this heat pump, and that the optimization method will optimize and find the correct combination of your selected heat pumps for your particular project. So stay tuned for that as well. Now, the third, perhaps most important update we're working on has to be the variable emission temperature. Now, in the backend, depending on heating and domestic hot water, the heat pumps produce water at 35 or 55 degrees by default. Now, I know there are systems where you need 45 degrees as an emission temperature for your heating, or you need 60 degrees for domestic hot water, and we are working on making it possible for you, the user, to enter at which temperature you want your heat to be emitted to the building. We're even working on methods of making this emission temperature a function of the outside temperature. So also stay tuned for that, because it will again dramatically improve the efficiency of your geothermal system calculation. And lastly, now the heat pumps of NRAD are already implemented, but we are working with other manufacturers as well, and more heat pumps are in the pipeline to be implemented as well. So perhaps when you're watching this video, the list is already quite a lot longer. So this was basically everything I wanted to say in this video. I hope you found it interesting. It marks the end of a 3-part series to making GHEtool significantly more accurate. We are working on a new series, which we will talk about in a couple of months, probably. But I would say try this functionality, see what extra insights you can get. We're looking forward to your feedback, and I'm looking also forward to seeing you in our next video. Take care. Bye.